Hi, Chris Kuzmo here. Today we're going to talk about red-black trees. There are some perfectly decent videos out there, but there's one or two things that I would like to share about red-black trees in a slightly different way. First, we'll begin with what everyone does, the formal definition of a red-black tree. There's five things about red-black trees. One is they are binary search trees. So you can do all the binary search tree operations on them, or that is to say, if I give you a red-black tree and you treat it like a binary search tree, you won't necessarily notice or care. However, there will be added information for each one of the nodes in the tree, and that's item number two. Each node is assigned a color, either red or black. The third thing is that every leaf node in a binary search tree, in a red-black tree is black. The fourth thing is that if a node is red, then both of its children are black. And finally, the fifth and least intuitive idea is that any simple path from a node to a descendant leaf has the same number of black nodes. And that fifth one is the sort of the tricky one that you can't just fix up by changing the color of a node without thinking about anything else. So let's look at some examples. Here we have a binary search tree because the nodes are ordered in a way that obeys the binary search tree property. Every node to the lower left is smaller, every node to the lower right is larger, and every node is also either red or black, where we assume that this sort of dull gray is actually black. If I made them black, you can see the numbers, or I have to change the numbers, colors. So I just decided it would be easier to have black be this grayish color instead. The other constraint is that every leaf is black. So if we look at this tree, that doesn't satisfy the requirement. And so we can just go in and arbitrarily change the color of this particular so-called red-black tree so that its leaves are all black. Now this tree does satisfy the first requirements, but the next requirement, every red node has two black children. That requirement isn't satisfied because node number 6 here is red, but it doesn't have two black children. So we turn it to be black. So far, just going in and whenever a node breaks the rule, we can change the color of the node. And a particular node is all we have to look at, maybe its children, to determine whether or not it's satisfying the requirements for binary search tree. But now every simple path to a leaf that has the same number of black nodes, that requirement is a little bit more complicated. In our example, we can fix this. And what I mean by this is that let's consider node 11 here. If we go from node 11 down to node 8, we've got, if we count node 11 as being one black node in the path, that number remains 1 when we get to 8 because 8 ain't black. But to 6, that makes it when we go to node 6, that makes it so that we have 2 black nodes. When we go to node 5, 3 black nodes in that path. So 1, 2, 3 this way, 1, 2, 3 this way. Lovely, everything's great going left and going right. 1, 2, 3, 4. So we break the rule. Well, there's a number of different ways we can fix this, and the way that we fix it in our example is we make node 15 red, and that's fine because its children are black also. So this satisfies this is a legal red-black tree according to all the rules. However, we don't have satisfaction right now because there's no real sense that we can necessarily keep these properties after we've inserted a new node. And so in future videos, we'll concern ourselves with meeting that requirement.